Good morning, good afternoon, good evening. Welcome to the presentation of the reference software of television media analysis. I will say a few words about MPAI, which has developed this the specification, and then we'll see the reference software. So we are moving picture, audio, and data coding by artificial intelligence. We are international, unaffiliated, not-for-profit, standards developing organization. We develop AI-based data coding standards. And importantly, we try and attach clear intellectual property rights licensing framework to our standards. So this is giving more detail about making standard accessible and timely available, which is the third of the goals that I mentioned. Before initiating a standard, active principal members, because we have principal and associate members, develop and adopt the framework license. And this is not a license really, because it does not have values, dollars, percentage, dates, but it has some important elements. In particular, this declaration that the eventual license will be issued at a price comparable with similar standard technologies and not after products are on the market. During the development, any member making a contribution declare it will make its license available according to the framework license. And after the development, members holding IP in the standard select their preferred patent pool administrator. So this is slightly complicated, but it's important because developing a standard is a critical thing. It must be done with a very clear and rigorous process. Our process has 8 steps. First, we develop the functional requirement, then the commercial requirement. The framework license. We issue a call for technologies. We develop a standard based on the result of the code. And before the standard is ready, we publish it for community comment. And finally, we publish the standard in final form. MPAI standards make explicit the computing workflow of AI application. An MPAI standard breaks up monolithic AI application into smaller subsets which have known data semantics. So what they exchange has, to the extent possible, have a known data semantics. Developers compete offering improved performance standard components, and humans can select applications whose internal operation they can somehow understand. So this is the critical point of AI. So that's AI is great, but what's happens inside? We try and give an answer to users for that. So in summary, MPAI AI standardization is component-based. When AI application is subdivided in smaller components, they are called AI modules, aggregated in one or more AI workflow, AIW, and executed in a standard environment called AIF. And this is what is included in the first foundational technical specification called AI framework. So this is the reference model of version 2.0 of MPAI AIF. You see that we have AI modules. Together, they are included in AI workflow. We have APIs to access a controller, and then we have other APIs in particular for security. The next point is that when you create a standard, particularly when you create several standards, you create ecosystems. And each ecosystem is composed of developers, integrators, consumers. We have identified as the MPAI store the entity that guarantees that the The components, AI modules, and AI workflows are interoperable, trusted, and available. So this is the task of the second foundational specification, governance of the MPAI ecosystem. So here is a graphical representation of the MPAI ecosystem. We have MPAI that issues standards. Then we have implementers taking the standard, developing implementations. We have performance assessors, and an implementer can submit implementation to performance assessor. Imagine that the answer is yes, saying that it is, the performance is adequate. Then the implementer can submit the implementation to the MPAI store, which verifies the security, test the conformance, and check the performance. And then the submitted components are posted on the MPAI store, where users can download the implementation and, if they want, report their experience score. So this is the organization. As you see, it's quite big because we are dealing with quite a few things. We have about 20 projects right now, and we have already produced 13 standards, and this is what you see. So we have 13 standards approved, and we have a few more that are under development for AI for health. We have it for server-based predictive multiplayer gaming, and we have for XR menu, and then we have other projects that have not reached the development stage. So with this, I will pass my presentation to my colleagues, Francesco and Mattia, please.
Okay, thank you, Leonardo. I'm here with my colleague Mattia. We are both from Eurix, which is an Italian company working on innovative technologies and on AI. So we joined the AIF group 2 years ago and started working on the definition of the second version of the AI framework and proposed this use case. So our quick demonstration for today is organized with a short presentation by myself to give you an overview of the solution that you implemented, and then Mattia will show you the system up and running. Okay, so I hope you can see my screen.
Yes.
Okay. Sorry, probably. Excuse me. I picked the. Sorry, I picked the wrong one. Just give me a second. Okay. That's it. Okay. First of all, very quickly, I would like to say a few words about the motivation for this TV media analysis. As I said, we are implementing the reference software for the second version of EAF specification. There was already a first version implementation for, let's say, embedded systems and the microcontrollers, and now we moved to enterprise systems, so distributed system of higher level. And for doing this, we also used the popular technologies that are used nowadays in machine learning field. So Python language, first of all, open source community models from, for example, Hugging Face and other communities, and containerization technology, Docker, which provides the possibility to easily distribute and also isolate each modules. So this use case originates from activities that we are doing in collaboration with the RAI Research Center here in Torino for implemented audiovisual content enrichment systems that they are using for automatic processing of news and other process programs. So this is integrated in their current digitization pipeline where they analyze the content and provide it to other systems. So we kept this idea and the use case and added some specific parts that are provided by MPAI. So from that original implementation, we moved to an MPAI compliant solution. In particular, AAF provided us with an architecture and the possibility to define in a standard way AI analysis modules, the so-called AIMs. They are integrated in a AI workflow, which in the following will be referenced to as AIW. And this results in a standard output in a JSON format, which is compliant, as we will see, to other parts of the MPI specifications. The idea is that this is a back-end application used to process systems, and the output can then be used for other system and scenarios. So having a standard representation, which is one of the things that, by the way, all the broadcasters and other systems are currently struggling with at the moment, is very important also for interoperability issues. Okay, so here you can see an overview of TMA. And by the way, if you go on the MPI website, you can find an extensive documentation of the implementation, of the description of all the modules, the way the software can be used, downloaded, and operated. So I will just give you a general idea here of how things are working, and then you can refer to the documentation for further information. So the main use case is based on the system receiving a television video file in input, producing intermediate results analysis for the so-called content enrichment using AI analysis modules, and then produce a JSON representation. In TMA, it ties all these modules together, and according to the version 2 specification, we used an events based architecture. So basically, the messages are exchanged among all the modules under the orchestration of the controller. And I will show you the overall AIF architecture in a moment. Here you see the sequence of all the moments. As you can see, there is a quite a big number of independent model, but one of the core ideas of the implementation is just that you can develop and plug your own module for a specific analysis and extend the overall pipeline. So each one of these modules runs in a dedicated Docker container, and we are using RabbitMQ, which is a very popular message broker for the integration. We also provided open source container manager tool, which is portainer.io, which is also used, that I will show you a screenshot in a moment. So here you can see an overview. This is taken from AIF specification. And you see on the bottom line the controller and the other common parts for the communication, storage, access, and MPI store in the specification. So looking at the flow, you can see that we start from an audio video file, then we have a component responsible for splitting the audio part and the video part. Streams, the audio part goes to the audio segmentation, which is used for the so-called diarization, so to identify all the different speakers in the program. And then having this information about the speech segment, we go with the speaker ID recognition using some speaker database that can be used. So we are able to identify the speaker in the program. The video part goes through a visual change detection component, which is basically detecting the change in the scenes of the program, and is also collecting the keyframes, so the relevant images within each shot, each segment, and the images and the associated time are used to make the face recognition, so to recognize people and so to connect them with the speaker in the program. From these modules, as you can see, we take the output of the previous AIMs and apply further analysis. You can see the audiovisual alignment, which is basically used to combine the visual part with the audio part to map the speakers with the faces. And then we have also the ASR component, which is the automated speech recognition part, which is responsible for the transcription of the text. Also, the text can be further analyzed. For example, you can extend the workflow with other tools for sentiment analysis or in general, any tools that can benefit from having the text transcription. Also, this can be used, of course, for search and for indexing information. And then we combine all these huge amount of pieces which are related to the video timeline, basically. We combine them into an audiovisual scene description. And then finally in audiovisual event description, which is, as I said, leveraging the MPAI representation. Here, just wanted to also provide an idea about also the connection with other parts of MPAI activities, because um, the TMA leverages the results of other working groups in MPAI, and here you can see also the references to the websites where you can find information. And in particular, there are groups MMC, OSD, and PF, which are also contributing to this, because we are using basically the current output of their specification. So we can define this TMA as a joint effort of the whole MPI group. And it was also very interesting for us to integrate into this workflow the contributions of other groups who are working on their scenarios and their use cases. So we can give a coherent integration of the results of all MPI contributors. Before moving to the demo, just wanted to give you an idea about also some of the technologies that we are using. You see here for the implementation that we are leveraging popular open source modules for example, the Whisper model from OpenAI, or deep face library for face recognition, or tools like FFmpeg. For some of the modules, we also used some benchmark datasets which are available from the community. And also, you can see in the last column on the right that although not mandatory, many of the modules, of course, can benefit from executing in an environment with a GPU, because you can definitely execute the model at full speed and parallelization, and leverage all the computing power. Of course, if GPU is not available, the performances will be worse, and also the processing time will get longer. all the information, the details again about the libraries and all this stuff is in the documentation. Okay, now I stop here for a moment so Mattia can just start with the demonstration and start also the processing, and then we will continue with the other second part of the presentation.
Thank you, Francesco. I'll share my screen. Okay. 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 Awesome. Okay. So basically, here you see a clone of OSD TMA, the orchestrator, say the module that controls the whole workflow. So inside the OSD TMA folder, you see the controller, and you also see another folder called storage. And in this folder, just give me a second. Screen. Okay, in this folder, you can see we have in bits and then another subfolder. We have a video file to be processed. You can download this file by following the instructions in the GitHub that you can find on the README, on the OSD TMA README. Okay, then you have other folders besides bits. You have a folder called confs. Here you have the configuration, the setup file for MMCA US, so the segmentation module. You can find, once again, instructions to download such a file from, you can find them on GitHub, on GitLab. And then you have data sets, same data sets as in the slide that Francesco showed before. So here you have a data set for speaker identification. Sorry, that's the wrong one. So yeah, you have, sorry, this one is the one for face recognition. Once again, you can find instruction to download such a dataset on the README, on the provided README, by reading it. And here we have added two folders. Actually, it's four folders with some faces to a data set called LFW, labeled faces in wild. Actually, that's just a small part of it. So we provided screenshots, basically, of a few in this case, speakers, let's say celebrities that we want to identify in our video, in our MP4. So that's just an example. Okay, going back a second. Okay, so so that's basically a subset of labeled faces in the wild. And then we have a subset of Vox celebrities with, with wave files of celebrities. Okay, so for instance, let's open this folder, and here you see wave files that we have downloaded from the internet that should help identify Bill Burr whenever he speaks. And we did the same for other celebrities that we want to identify. As you can see, this data set is, I mean, we just took a subset of the original data set and added a few folders to it. And it's pretty small because actually speaker identification takes a lot of time. To have a short demo, we try to have just a few folders of WAV files. This way, it takes a shorter time to identify speakers. Okay, moving back to storage folder, to the parent folder, we also have a folder called models. And here we have 4 models, mostly, as Francesco said, coming from Hugging Face. So you have models for 4 modules, and you once again you find instructions on how to download such models from the GitHub. Now, okay, so I'll just move back to here. Okay, so here you can see JSON file, and basically this is the input JSON that we're gonna feed to RabbitMQ, to the message broker, to start the workflow. So to do so, we use, give me a second. So to do so, we use RabbitMQ user interface. And you see here a list of queues. Each queue belongs to a module. Basically allows a module to get a message, a proper input message, and to output a JSON that is then fed to another module. And here, to start the whole flow, we copy paste that message here, the payload of a queue of the controller queue. It's called queue module controller, and we submit. We publish such a message. And now, if we go to container, you will see that okay, we started with 2 modules called controller and RabbitMQ, and now we have another module which is spawned, which is basically started by the controller. And this basically in a Docker in Docker fashion. So the controller runs each container based on the workflow that Francesco showed before. So if we go back to the storage folder. Okay, you can see that here we have the output of a few modules. You have the audio video split. So you have the WAV file, which is produced by splitting audio and video. You have scene change detection, visual change detection, and its output. You have the, sorry. Then you have the segmentation and its output. Of course, if you click here, you can see the JSON, which is coming out of, which is produced and saved by such a module. And okay, now you see also another folder, but the idea is basically that here you get a whole you get one folder per module. Whenever the module is done, it saves the output JSON in a proper folder with which bears its name. I mean, which bears the name of the module, and that's it. Up to the OSD AVE, which is the last module, the aggregator, the audio visual event descriptor, and yeah. So I'll leave the floor to Francesco. Okay.
Okay, so going back very quickly to a few more details about the implementation. Well, here you see a few advantages what we consider in the implement of this approach. Well, first of all, we are making extensive use of standards, in particular from the output of other MPAI groups, and also the output of the processing pipeline is straightforward because all the modules are integrated together and generating standard JSON file. All the components are running in an isolated container with some interfaces, their own APIs, which are dedicated for specific for that module, can be reused. So this modular approach favors the extensibility and also the possibility to execute the implementation locally or even in a distributed deployment. For example, if you remember the table that I've shown before, some modules can require for better performances the use of GPUs. So you could distribute some of the components on servers or cloud environments where they are empowered with such hardware acceleration and have other modules running on other systems, and then you can integrate. The system is basically platform independent because you can distribute all the components with the Docker. So basically you can run on any operating system and you have a variety of channels to distribute it. And I also want to stress again the importance of this output for the interoperability. Just to give also you an example of the visual change detection and the possible applications that could be built on top of the output of the system, you see here that, for example, we created this very simple visualization of based on the output of the visual change detection. The spikes here represent the scene change. And if you can follow the blue line moving across the line, you can see that based on the analysis of the video, the peaks correspond to video changes. So this can be integrated, for example, in other applications for quality control or video analysis or systems for the documentation and access of the system in the archives and other applications. One additional consideration about face recognition. There is plenty of libraries and systems that can be used. The MPAI specifications provides a way to represent the face bounding boxes and the information. These are all accommodated in the JSON output and are very general, so you can switch to also to other modules. For example, here you see the confidence level in the identification of the people, of the speaker, with the dimension of the face bounding box and the distance from the data set. So this information is also provided in the JSON output. And going into a few more detail of the output JSON, you can see some excerpts of the results. And I don't want to go through all the details, but just to give you an idea about how the video is decomposed in different structures. And you can see here we are pointing to other MPAI specification that are providing the way to specify the information for the different parts of the system. And of course, for example, if you look at the ASR specification, we can accommodate the whole video transcription, which can be useful for further analysis, as I said. And here you see what I mentioned before, a way of representing the face bounding box and the information about the system analysis. So the idea is that this JSON file should be archived along with the audiovisual material and can be used later on for documentation, for accessing, and for visualization. And within the video, we have references to the digital artifacts which are created, for example, the frames or the audio segments which are extracted. We include in the output JSON also the path to these files, so they can easily retrieved, inspected, accessed, and processed, or whatever you want. Here, just put just to give also an idea about the management tools that come with this simple implementation. Here you have a view of the Portainer interface. This is, as I said, open source and is running in its own container. From here, you have access to plenty of information about the status of all the containers, the resources that they are using, their status, and then you can also access the logging console to inspect the behavior of each module. And of course, you can also trigger the execution or the pause or whatever you want to do with the modules. In particular, you see here in this menu, which is provided here, we are implementing the part of the AIF specification, which inspects the possibility to manage the flow, to pause some modules, to restart, and whatever. Mattia has already shown a way to integrate with the system by sending messages, because this is an events-based architecture. We didn't provide a more, let's say, simple or usable user interface, because the idea is that that kind of interface will probably be integrated in other existing systems within an organization, such as in the case of RAI, and also should target the specific use case. But again, having the JSON representation and all the results, you can build on top of it your own graphical user interface. And I think that's it. You can find all the information on the MPAI AF page on the MPAI website, and you have some references. And also, as I said, the documentation of the software is also available, along with the source code, which is available on request on the MPAI GitLab. Thank you.
Thank you, Mattia and Francesco. As you see, this is really a very important implementation of many MPAI technologies, and the integration point is the AI framework, because that's what drives everything. So let me just show one more slide that summarizes what a few more ideas. So the first is that this is an implementation of the MPAI OSD version 1.1 standard, in specifically the television media analysis. And it is based on the AIF standard. It integrates neural network models that are openly available and integrate them in and make them AIMs, AIM that are standardized in their interfaces by the MPAI OSD standard. It describes audio and visual scenes and objects in a standard format. So this is the important part, that the output is in a standard format, JSON-based, and you can develop custom players to navigate the scene and event descriptor and a lot of other application, as Francesco has already suggested. So with that, we look forward to working with you on this exciting MPAI project. And remember that MPAI motto is share the fun and build the future. Thank you very much. Now we can close the meeting.